Hello, in this video we will be covering the sorting algorithm quicksort, its characteristics, a demonstration, and the code implementation. Quicksort. It's a divide and conquer recursive-based algorithm. This means that it's going to be separating the data so that it's easier to deal with, and it also calls on itself. It selects a pivot element to partition a given array. For this implementation, we will always choose the last element as the pivot. However, there are other implementations which will choose other elements as the pivot. The partition method places the pivot element in its correct position, while putting the smaller elements before it and the larger elements after. This means, depending on the pivot that the program chose, your runtime could be affected. Quicksort also creates subarrays. This is so that it can deal with the data more appropriately. And here are the complexity, or the runtimes. For most quicksort algorithms, the average case is usually the most common one, which is big O n log n. Now we have an example of our first quicksort call. Here we have the method that we actually call. From there, it'll call the actual quicksort method, which will take the array A, the beginning and ending index of the array we wish to sort. Here we have some pseudocode. This is the pseudocode of the actual algorithm, which we have in the bottom left corner. Next, we have our test array of 7 integers, and also our first and last. Starting on line 3, we have the quicksort call. We pass the array A, the starting index, and the ending index, or 0 and 6. We can now go to the pseudocode of quicksort. The first thing that we will check is the first and last. Since we are dealing with a recursive method, this is our base case. Our base case will be met if first is greater than or equal to last. Essentially, this means that we're trying to sort an array of size 1, because first and last are pointing at the same element. Or first has gone past last, so that there is no elements left in the array to sort. If the base case is triggered, we'll simply return. As for the recursive case, which starts on line 8 of the pseudocode, we'll call our partition method, which will take an array A, our array of ints, int first, and int last, which are our indexes. The method will return an int, which we will store in the variable called p. We'll go more into depth with the partition method later. After the partition, we'll call quicksort on the left half of our array, then the right half of our array. On our first quicksort call, first is equal to 0 because it is the first element in our array, and last is equal to 6 because it is the last element in our array. Our base case is checking if 0 is greater than or equal to 6, which turns out to be false. So we move on to our recursive case. The partition method is called, passing the array of ints, first and last, as parameters. Here we have a demonstration of our first partition call. We have the actual code here, pseudocode, and the array that we'll be using, and also our variables. The first step in partitioning our array is picking a pivot element. There are multiple ways of picking a pivot, but for this implementation, we're choosing the final element in our array. In this particular case, element 6 is our pivot. The goal of the partition method is to divide this array into 2 groups. The first group are numbers that are less than the pivot, and the second group are the numbers that are greater than the pivot. In the end, the pivot will go between the 2 groups. This will become clear in the middle of our algorithm, opposed to the beginning. To run this algorithm, we need the 2 indexes I and j. J will keep track of the current elements we are examining, which is part of a for loop. The for loop is telling the computer to move j from the beginning of the array up to, but not including, the pivot element. In each iteration of our for loop, we are checking if all the numbers we've seen so far are separated into 2 groups. The first group are numbers that are less than the pivot, and the second group are numbers that are greater than or equal to the pivot. For our first iteration, we compare 23 to 3. And is 23 less than or equal to 3? No, that's false. Moving on to the next element, we have j equal to 1, which is the element 15. We check if 15 is less than or equal to 3, which is false, meaning that j moves forward, and we now have j equal to 2, which is the element 1. Since 1 less than or equal to 3 is true, this means that we're going to increment I, then swap a at I and a at j. I is set to 0, and then we swap the values. I will always point to the last number of our first group that is less than the pivot. This means that all numbers from the beginning of the array up to I should be less than the pivot. If in the case that j is less than the pivot, our algorithm will increment I by 1, then swap I and j as seen. Now we continue traversing through the array, comparing element j to pivot until we reach the index before the pivot. No other swaps will be made. We continue traversing through the array, comparing the element j to the pivot until the index is reached right before the pivot. Moving forward, we'll go back to line 12. J will move forward, meaning that it is now equal to 3. And now we have, is 15 less than or equal to 3? False. This means nothing happens, and j will increment. J is now equal to 4. And we have, is 30 less than or equal to 3? False. This means nothing happens, and j increments. J is now equal to 5, which is the index right before the pivot. And we have, is 8 less than or equal to 3? False. We can now move to line 15 and swap A at I plus 1 and A at pivot. Then the final step is to return I plus 1, which is 1. Now that we return to our quicksort method, the next step in our recursive case is to call quicksort on the left half of our array. We pass the array A, int first, then p minus 1. This just means that we'll be sorting the elements up to p. For this call, we're passing first as 0 and p minus 1 as 0. Here, we can actually see our base case in action. Since first is less than or equal to last, we simply return. Next, we call quicksort on the right half of our array. We pass our array p plus 1, which is 2, and last, which is 6. Now we sort our right half. The first step is to check our base case. 2 is not greater than or equal to 6. This means we can continue on to our recursive case, calling the partition method again, but this time passing our array first, which is 2, and last, which is 6. Here, we repeat the same set of instructions as the last partition call. We traverse through the beginning of our array first up to the element before our pivot. While we do this, we compare the elements j and the pivot. First, we initialize our variables. I is equal to first minus 1, which is 1, and j is equal to first. We can then begin the comparisons. We have, is a at j less than or equal to a at pivot? Or, is 23 less than 15? False. This means nothing will happen, and j increments. Now we have j equal to 3, and we check, is a at j less than or equal to a at pivot? Or, is 15 less than or equal to 15? True. This means I will increment. Setting the new value for I, we then swap a at I and a at j. We can now begin again. J is set to 4, and we have, is 30 less than or equal to 15? False. This means nothing happens, and j increments. J is now equal to 5, and we check, is 8 less than or equal to 15? True. This means that we increment I becomes 3, and then we swap a at I and a at j. We then swap a at I plus 1 and a at pivot. Then we return I plus 1, which is 4. If we take a close look at our array now, the separation of the two groups is becoming clearer. Numbers less than the pivot are on the left side, and numbers larger than it are on the right. The next step that follows our recursive case is calling quicksort on the left half. We pass array A, 0 for first, and 3 for p minus 1. Here, the procedure is the same. We check our base case. Is first greater than or equal to 3? False. This means we don't return, and we continue on to our next partition method. Here we pass the array A, first as 0 and last as 3. Here, the procedure is the same. We initialize I and j, and then test it. Is 1 less than or equal to 8? True. This means that we will increment I will now be equal to 0, and then we swap I and j, which happens to be 0 and 0. Moving forward, we increment j, and it is now equal to 1. We check, is 3 less than or equal to 8? True. This means we increment I again. I is now equal to 1, and we swap I and j. And now we check again. After incrementing j, we have, is 15 less than or equal to 8? False. We've also reached the index right before a pivot, which means we're going to swap a at I plus 1 and a at pivot. Doing so results in the array that we wanted. After that, we return I plus 1, and the array is sorted. I hope this is helpful, and happy coding. Here is the code implementation for the algorithm. First, I'm going to make a class. And now I'm going to create my main. Now inside my main, I'm going to create the array. For the algorithm of quicksort, there are two methods that we have to make. So I first will create the quicksort method. This is the recursive method, so we need to make sure that we create it with a base case. Just like in the demonstration, this method will take the array of first and the last. For the base case, we will have an if statement, and if it is true, we will return. The base case only happens when the first is greater than or equal to the last. However, if that is not the case, we have our recursive case, which is the partition, which we will create here in a moment. Remember, partition takes the array first and last. After the partition, we have the left call, which is a recursive call to the left side. So it will look like quicksort a first, and then last will actually be p minus 1. And for the right call, we'll have quicksort a p plus 1 and last. That is all we need for the quicksort method. Now we can create the partition one. Remember, partition does return an int, so that will be our return type. Partition will take the array, the first, and the last. First we're going to make our variables, which will be the pivot. Just like what we said in the demonstration, our pivot will always be the last of the array. And int I will be equal to first minus 1. Now we will create the for loop, which we will traverse through the array with. Inside of the for loop, we will have an if statement. This if statement will only happen when the array at j is less than or equal to the pivot. Inside of the if statement, I will increment, and we will create a temporary variable to do a swap. Now that that's done, we get outside of the if and the for loop, and we can do the final swap, which we will have to create another temp for. Then after that, we will return I plus 1. With that, everything should now be completed, and all we need to do is have a call and print. We send the array first, which is index 0, and last, which will be the array length minus 1. Create a quick print. Make sure to save, confirm that my terminal is in the same directory, and now we can compile it, look for any errors. There's none, so we can go ahead and run it. The result is a sorted array. I hope this was helpful, and happy coding!